Okay. Turn off the transcript. Okay, so welcome back for the last hour, the third hour of this first lecture. So we have now just talked about how to solve case number 1, where we got this this very nice velocity profile. We can say that this is the solution for case number 1. Of course, now the question is, what would be the solution for the Couette flow if we had looked at case number 2? Again, just to remind ourselves, case number 2 was like this, when the origin of the coordinate system was at the lower wall and the upper wall was moving with a velocity of 2 uw. Well, if you now go into the calculation, and I'm kind of hoping that you would do that as a homework. If you do that, you just have different boundary conditions. You had u at 0 being 0, and u at 2h would then be 2uw. Well, and if you now do the calculation, what you will actually get as a result is that u as a function of y would essentially be exactly the same result as before, namely uw divided by h times y. So that's also for case number 2. Now, how can we understand that? Well, in case number 2, essentially the only difference is that that's actually wrong. The only difference is that my origin of the coordinate system would be here, x and y. So this is for case 2. And then my velocity profile, and I'm now taking the purple, would kind of develop in that way that we had 0 here, and my velocity would kind of look like this. And it would, of course, go to a value of 2 uw here on top. And that is what I would get for case number 2. But the main result, namely that the velocity profile is linear, that is of course the same in both cases, and that is one of the main features that you should remember in Couette flow. So this simplest shear-driven flow, the velocity profile is linear. The laminar velocity profile is linear. That's also something I would like to write down. So we have a linear velocity profile. Now, if I just summarize the other points that I mentioned now a few times, namely that this particular flow is said to be shear driven as opposed to pressure driven, as we will see later on. And the last comment that I would like to make here is kind of a physical explanation of what's actually happening here. And what we can say is that we have a situation where momentum is injected into the flow domain, is injected from the walls. Well, momentum is injected from the walls. That means, well, because I move the walls and because I have no slip boundary conditions, I have momentum added to the flow, which is then, it has to do this momentum has to go somewhere. And what happens essentially is that this momentum is then transferred by the viscosity, so by viscous forces, towards the center of the channel, towards the center of the channel, or the channel. So this is essentially what happens. I inject momentum by moving the walls, And this momentum is then diffusing or transferred by viscous forces, which is kind of, that's what we mean with diffusing. Maybe I can actually, right. This is diffusing into the wall. And the solution at the end, after a long time, is kind of the steady state of a diffusion equation, which is just a linear profile. So this is what we get as at the end. Okay, so now we have solved this Couette problem, and of course it was very easy to solve at the end because it was just I mean the only difficult part was to solve a second order differential equation, but that was of course just was very easy to do. And we also have a physical interpretation of what's actually happening. But we're perhaps not at the end yet, because we should now also talk a little bit about kind of a force balance, or forces that are acting in this particular case. Forces, particular frictional forces, so friction between the fluid and the wall, are of course very relevant. I mean, I mentioned it in the beginning when we looked at this airfoil. The viscous drag, or the drag in general, of an airfoil is of course one of the important design parameters, and in the end the viscous drag is a large part of that. I mean, in an airplane it's on the order of 40% of the drag that is actually caused by viscous forces. So understanding on how this momentum transfer is working, and in particular how this momentum transfer will also influence the friction, is very important. So that means the next thing that we need to look at is the interaction between the wall and the fluid. And this interaction essentially means that there is some sort of force that will arise there, and this force in the case of Couette is, or means that there is a force needed such that we can actually move the walls. So the fluid will somehow exert a restricting, or a force against moving the wall. And of course, this is what we call the wall shear stress, and it's typically denoted as a tau wall, or tau W, which is nothing else than the viscosity times the wall gradient. So du dy at the wall. And of course, now in the case of Couette, we can just go into our equation that we have for u as a function of y. So we can evaluate this du dy, and if we do that, we get mu times uw divided by h. So this is now what we call the wall shear stress. So this is the stress that is exerted by the fluid onto the wall. And well, if we now look at the units of this whole thing, well, it really has the unit of a stress, which means it's a force which is measured in Newton divided by an area. So Newton divided by meter squared, and of course that's the same unit as Pascal, although of course Pascal is mainly used for pressure. But it's in the end, it's the same physical meaning behind it. The pressure would then just be a normal stress, and in this case it would actually be a shear stress, because it's the force is not normal to the plane that we consider. Yeah, so this is the wall shear stress. The tau wall is mu times uw divided by h. Now, as you know, in fluid mechanics, we like a lot non-dimensional numbers. So we would like to kind of do something in a more general way. So we would like to introduce a non-dimensionalization so that we can actually compare different Couette flows with each other. I'll tell you later on a little bit more what what I mean with this generalization. But for the time being, let's just think of how could we kind of simplify this expression into a non-dimensional or a general form. And for this, we introduce something that you all know. So let's introduce a Reynolds number. And that's typically abbreviated with RE. And of course, Reynolds numbers, that's, I guess you all have heard about that. The Reynolds number is, I think, by far the most relevant non-dimensional number in fluid mechanics. Everything depends on the Reynolds number. There's no flow, I mean, of course there are, but there's no kind of technical flow where the Reynolds number or variants of the Reynolds numbers are not important. The definition is, I mean, you can define it in various ways, and we will do that later on as well. For the time being, I think the easy way to just remember that is that the Reynolds number essentially can be viewed as a length scale times a velocity scale divided by the kinematic viscosity. As I said, I will discuss later on in more detail what it really means. You know, the ratio of viscous forces divided by advective forces. But for the time being, just think of it as being a length times a velocity divided by the kinematic viscosity. You can of course also write it when you take mu and rho in, so it's mu rho divided by mu times L times U. Now this L and this U, they are to be considered characteristic length and velocity scales for the problem at hand. And in our case of Couette, what could be relevant velocity and length scales? Well, let's just go to the sketch again, because it becomes actually quite easy to see. Well, what are relevant velocity and length scales? Well, it actually turns out it's really very easy. There is just one velocity scale, UW, appears on both sides. And there is just one length scale, which is the separation. And we actually take the h here as the length scale. So in this case, Couette flow is fully described by specifying one velocity scale and one length scale. And I guess now you start to see why the Reynolds number is so useful, because it's exactly these two scales that we can now supplement here, together with the description of the fluid, which is the viscosity. So in this case, it would be clear that what we need to choose would be this UW times H divided by mu. And really, the reason for that is that UW is the only velocity scale that we have. The H here is the only length scale that we have in the problem. And the nu here is something that describes our fluid. And for us, it's mainly the viscosity that is relevant. That's why the viscosity is important. So now we actually have a way of describing the Reynolds number relevant for our problem. It's UW times H divided by nu. Also here, some quick historical background. The Reynolds number goes back to a person that is called Osborne Reynolds. And he lived 1842 to 1912. And the definition, or the first time that he actually introduced the Reynolds number, in fact, he obviously didn't introduce the Reynolds number. what he introduced was a number that was actually the inverse of the Reynolds number. So you can view it as a non-dimensional viscosity because it was nu divided by length and velocity scale. So he non-dimensionalized the viscosity. And this actually goes back to an 1883 paper. And I would just like to, let's see whether this actually works. I would like to very briefly show you how he actually came up with the Reynolds number, because I think it's quite interesting to discuss that a little bit. So, okay, how it actually works. So this is an illustration taken from that particular paper, from the 1883 paper. And what you can see here is that you have a domain, this box here, in which you want to, or Reynolds wanted to look at the fluid flow. And actually what he did is he wanted to look at the flow inside this pipe here. So there was a thin pipe, a glass pipe, in which he wanted to observe how the flow is moving. And how he did that, he had some supply of water to kind of move here, and then he was injecting via this apparatus a little bit of dye, a little bit of color into this pipe flow. And what he wanted to study is how this dye is actually changing as the flow rate was changed of the flow in the pipe. Also here there's a few pictures which I just want to show you. So, like this. So these are three pictures that are taken again from this paper. The first one here, this one was taken at a low Reynolds number, and this one was taken at a high Reynolds number. And this one here was a kind of a snapshot, like a short exposure time. And now the relevance here was that he, as I was saying, he was changing the flow rate, which of course means in terms of Reynolds number, he was changing the velocities. He was increasing the velocity, meaning that the Reynolds number went up because the length, that's kind of the diameter of the pipe, was constant, and the viscosity was also constant. So he was changing the Reynolds number while doing his experiment. And then what he saw, that's kind of the purpose of this study, and it's actually quite interesting that the whole paper can be, if you wish, be summarized by just reading the title. It says that an experimental investigation of the circumstances which determine whether the motion of water shall be direct or sinuous, and of the law of resistance in parallel channels. Well, what he wanted to do here was the following. He wanted to see what happens with the flow when you increase the Reynolds number, and he saw that, okay, at first it was straight, and then at some point it became kind of oscillatory, and he wanted to see what influence this has on the resistance, the pressure drop that you, or the pumping power that you need to put in. And then, well, the result was that he could see that it actually doesn't depend on the flow rate. It depends on the ratio of L time, or of the product of L and U divided by the viscosity. That's what is important. So that's the origin of the Reynolds number. Okay, but what does this have to do with us right now? Well, we have now introduced the Reynolds number in the way that it's done here, and as I said, you can view it, at least for now. We'll talk more about that later on, but for now you can view it as a non-dimensionalization of the viscosity. Okay, well, because we like non-dimensionalization so much, we can actually also look at the non-dimensional skin friction coefficient. Skin friction coefficient. Well, also that is something that you probably know. This is called CF. That's just a non-dimensional skin friction. Well, so that means we take our skin friction that we have defined up here. We realize that this has the unit of Newton, or it's a unit of a stress. So that means we need to divide it by something that also has the unit of a stress. And what we take is 1/2 rho times the velocity squared. Of course, this is an expression that you probably remember from the equation of from the Bernoulli equation. That is nothing else than the kind of the pressure term, the static pressure, the dynamic pressure term. And of course, unit-wise, this makes sense because both of them have units of Newton divided by area. So this is a non-dimensional skin friction now. And well, now I can go on a little bit. I can take the expression for tau w that we have introduced above. So this one here, nu times uw divided by h. So we get something like this. Mu divided by rho. Then we have 2 uw divided by uw squared times h. So I just put in the expression for tau wall. Well, now if I'm simplifying that a little bit, what I will see is I will get mu divided by rho. Then I get 1 over uw times h, and then I have a 2 left. And of course, I guess you see where this is going. This one here, that is nothing else than the Reynolds number that I have introduced here, or here. So this is just the definition of the Reynolds number. So that means now, and that's the interesting result, that CF in Couette is nothing else than 2 divided by the Reynolds number. So that means now that I have found a law that relates in a very general way the skin friction to the Reynolds number. So whatever velocity, whatever h I have, I can directly tell you what the CF is. It's 2 divided by Reynolds number. And of course, that also makes sense if you now go a little bit deeper into the equation. So let's just see what happens if the viscosity goes up. So if I increase the viscosity, well, that means that the Reynolds number goes down, you get a lower Reynolds number. And of course, that means that in consequence that CF, well, goes up. And I guess this kind of makes sense that as soon as I'm using a more viscous fluid, so if I go from, I don't know, from water to honey, well, I guess I need to work more to have the same speed. So that kind of makes sense. A little bit more interesting, perhaps, is what happens if I increase the speed. What happens then to the friction? Well, if I increase the speed, my Reynolds number goes up, and of course that means that my CF is going down. And of course, now you could wonder, why would that be? It's still a linear it's a linear velocity profile. So why would it mean that I need less friction if I increase the speed? That doesn't make sense. Well, it actually doesn't make sense. That is true. Is there a problem with my internet? Okay. And of course, I mean, you're absolutely right that this would not make sense. But the point is that the reason why this is actually the case is because I'm talking about non-dimensional friction. So it's CF, which is the shear stress non-dimensionalized by exactly the velocity. So that means that the non-dimensional CF goes down, but actually perhaps the friction in reality would actually not go down, because you need to multiply CF by, by UW squared. So that would actually mean that the actual friction goes up. And of course, that also shows you that it's a little bit dangerous when only considering non-dimensional numbers, because there's many things going in. It's this UV and areas and so on that are important. But of course, formally this is it's correct. But I just want to mention this here, that this is due to the non-dimensionalization. Non-dimensionalization of the problem at hand. Okay, so this is this was very good. Another observation that we made is that at the end, it's only the Reynolds number that is left to determine the friction. So only a Reynolds number remains. Also this, I would say, it's actually not surprising. I think at the end, everything else would have been surprising, because as I was saying in the beginning, the Reynolds number is the only thing that actually determines the flow conditions in this case. So it would be very strange if the non-dimensional friction could not be described by just the Reynolds number. Okay, and the last observation that we can also make from here, that has again to do with the Reynolds number, namely that the friction is actually linear in the flow speed, or the flow velocity. So if I double the speed, the friction will change linearly, and that's as I said, this is kind of an expected behavior for laminar flows. This is typical for laminar flows. Again, keep in mind we're talking about CF now. The actual friction needs to be multiplied with the velocity squared.
Sorry, Professor.
Yeah.
Can you hear me?
Yeah.
How the friction coefficient would change if we don't have a non-Newtonian fluid? Like the and the
yes,
other.
yes. Well, that's of course. I think that's an interesting question, and obviously, I guess you know the answer, because then suddenly your Navier-Stokes equation. I mean where do we have it? I mean your viscous term here would not look like that, right? I mean this viscous term would not look in this way. So it's not a linear shear stress relation anymore. And of course, that means that, first of all, already your velocity profile would look different. So you had to recalculate your velocity profile for all types of velocities, in particular if you have a nonlinear relation there. Then your shear stress, which you have calculated, I mean, your velocity profile would be different. So that means your shear stress here would also be different, maybe with a nonlinear relation. And so that means at the end of the day, this one would look different. So that means that this linearity that I was just mentioning here, this one would yeah, I think what is important here to say that this is for Newtonian fluids, let's say. For non-Newtonian fluids, of course, yeah, it would really look very different. Now, why do we care about, or why do we mainly care about Newtonian fluids? Well, of course, because it's easy. It's much easier to calculate with. It's an easier relation that, you know, it's the same for everything. So as a canonical flow problem, it's probably the best to work with. And of course, the two fluids that are, you know, all around us, air and water, they are actually very good approximations of Newtonian fluids. But of course, as soon as you go into, let's say, I don't know, the industry of you know, making food, for instance, where you have to deal a lot with, I mean, mayonnaise and toothpaste, and you know, the typical examples. Then of course this is not good anymore. Blood flow, as blood is not Newtonian. But this really then depends on the type of flow of fluid, shear thinning, shear thickening, and so on. So yeah, I don't know. I guess I didn't answer very much, but apart from saying that of course this is only valid for Newtonian fluids. I hope that's okay.
Okay, thank you so much.
Okay, then I would actually like to soon stop for today. There's one last thing that I would like to show you here, and that I would like to start with a plot, because now, of course, we can plot all of this in a figure, and typically what one plots here would be CF versus the Reynolds number. Now, in order to make these plots kind of, you know, easier readable, we typically plot them in a log-log fashion. So we put the logarithm of CF versus the logarithm of the Reynolds number. And of course, if you do that, then this shear stress relation CF is 2 over Reynolds becomes very easy. It just becomes a straight line. So this would be 2 divided by Reynolds. And of course, this is, as we were saying, this is proportional to Reynolds to the -1. In a log-log plot, this gives you a line with a slope -1. And this is in the laminar configuration. Now, as I was saying a few times, and also what Reynolds was considering, not everything is, of course, laminar. And I would like to now start or ask you one question. I guess it's a very simple one, but still perhaps relevant to just understand. So if you compare the friction factor CF, so this the non-dimensional friction that we calculate, for a laminar flow, so the one that we talked about, where everything is kind of straight, and for a turbulent flow, which one is larger? Is it the friction factor for a laminar flow or for a turbulent flow, or is it even that they are equal at the end? So what happens, essentially the question is, what happens to CF when you go from laminar to turbulent? So which one is larger? Okay, so there's 15 answers. This is the last thing for today, so don't worry. So, okay, yeah. So it's kind of roughly 50-50 in your answers. Actually, it's a majority that say that the friction factor for laminar flow is larger. Well, it's actually a trick question, because the question is not well posed. It's not a good question, because, and that's what we will discuss in much more detail on Friday, so for the second hour. Well, what happens now if I suddenly become turbulent? So what happens if I do as Reynolds did, I increase the Reynolds number? Well, at some point, actually, I will leave away from this line, the straight line, And it will actually jump up to another value, which then maybe looks like this. So I will get to another straight line. And the slope of this straight line is typically a little bit lower than what I had for the laminar flow. So typically on the order of, I don't know, 1 divided by 5 or, 0.2 or minus 0.2, something like that. So the slope is less. And in this region here, when I actually go from laminar to turbulent, so in this region here, I would actually go up in terms of friction factor. But of course, so this would be here, turbulent. But of course, the reason why I'm saying this was a trick question or kind of a bad question is, of course, the friction factor here is lower than, is larger than here. So you could actually argue that, it depends on how you compare. If you compare like this, then the friction factor for a laminar flow is larger than for a turbulent flow. But if you would compare kind of vertically, you could say if this is the laminar one and this would be the turbulent one, then it would actually increase. But I think it's actually very good how you answer, because it's not fully clear what is larger and what is lower. It's really depend. I would have needed to stay for the same flow rate, is laminar or turbulent flow having a lower CF. But of course, that's also kind of a strange question, because you cannot just choose whether you're laminar or turbulent. Or, I mean, sometimes you can with flow control, for instance, but not always. Okay, but I think this is where I would like to stop for today, and we will continue on Friday again from 3 to 6. Essentially, we will directly continue with friction and wet flow and so on. Are there any questions that you would like to discuss or ask? If not, then I would like to stop for today.